Hello everyone, welcome to today's webinar, Outcomes of the ICC Tall Wood Building Ad Hoc Committee, Tall Mass Timber Provisions in the 2021 I-Codes. I'm Paul Coates, Southeast Regional Manager for the American Wood Council. One of the presenters today, our other one will be Jason Smart, Manager of Engineering Technology for AWC. We're glad you're here. The picture on the front here is the Brock Commons student housing in Vancouver, Canada. It's an 18-story tall mass timber structure. You will receive AIA and ICC credits. Here's some of that information if you need to refer to it later. Really what we'll talk about today is what is the ICC Ad Hoc Committee on Tall Wood Buildings? Why was it formed? What did they do? Finally, what's the final result or the near final result? Because there are still code changes ongoing in this code change cycle this year. The main focus of the learning today will be knowing about the committee and something about its process, getting a fundamental grasp on the new construction types as they will appear in the 2021 IBC. That includes their allowable heights and areas, of course, and finally, how appropriate fire resistance is going to be accomplished in these buildings, new provisions for the protection of mass timber with gypsum, and how it will contribute, the gypsum and the non-combustible protection will contribute to the required fire resistance. We'll learn some other things today as well, especially you'll learn some of the background testing. Jason Smart is with us. He's going to be co-presenting, and he'll be going through what happened in the testing and some of the other fundamental code requirements after I give us this introduction. Here's a poll question. I'm going to turn it over to Marcy Weber, and she's going to lead you through the poll. There's no wrong answer to this one. This is kind of a test question, or a test of the test questions. So please pay attention to Marcy. Thanks.
There we go. So what is your profession? Easy one. So no matter what you do, we are happy that you are here. So as oftentimes, most of our audience is engineers, but we're delighted to have a variety of you here. So. And as always, I wait until about 80% or 30 seconds, and I've got both. So I am going to close the poll and share the results here. So 70% engineers, 16% building code officials, and just a little bit of everybody else. So welcome, everyone.
Great. Thank you, Marcy. And welcome, everyone. Here's an outline for the day. I'll start us off with a little background, a perspective on why a new category of construction called mass timber has developed, a little bit about the old and new engineered wood products involved, and especially about one in particular, cross-laminated timber. We'll move on then to the ICC Tall Wood Building Ad Hoc Committee itself, which the ICC Board of Directors set up to make sure the ICC codes addressed this new system appropriately. Intuitively, we all knew that with these new systems, it seemed like the current code requirements that are based on repetitive member framing, traditional joists and studs, that was the assumption under the current code requirements, was not going to be adequate for this system in terms of parameters and performance. So the committee, we'll talk about the committee and its genesis, its work, and the last four items in the outline are the work of the committee. Jason will start in on them, I'll finish them off, ends with building sizes. You could say that these kind of buildings here are the predecessor to tall mass timber buildings. These are traditional heavy timber buildings, type 4. These have a long history in many cities and towns across the country and in North America. Most of them are still serving well. They were constructed of solid sawn heavy timber beams and columns. Exterior walls of these buildings are usually non-combustible masonry. With few exceptions, they did not have many concealed spaces. They served well for utility as well as safety in downtown areas of cities. This is the prototype, you could say, for, or the pattern around which the current Type 4 heavy timber construction type was established in the code. Here's a newcomer, the star of the show for mass timber buildings, cross-laminated timber. It represents a sea change in wood construction because of its structural and fire resistance capabilities. They are going to be very different than traditional repetitive member light frame, conventional frame. CLT, as I'll refer to it, is typically dimension lumber, 2x lumber, laminated in layers, laid up in crosswise fashion, layer upon layer, to make a solid wood floor, solid wood wall or roof. These mass timber panels can be up to 20 inches thick, as long as 60 feet, whatever can be transported down the highway. This one shown here is about 10 inches. So imagine a building put together as shown on the right, which is a schematic of an actual building in London, Stadhouse building. And you can see that the structural capabilities are going to be far different than traditional repetitive member framing. The fire, you'll see from today that the fire resistance characteristics are also very different. You can see on this slide a little bit of the history of the development of cross-laminated timber, first in France, then Switzerland, Germany. In 1995, press technology developed, making manufacturing easier, more precise. Multi-story buildings in the last years of the 20th century, and then in the first decade of this century, European builders expanded the use of CLT significantly. Regulatory programs and incentives in Europe are what drove this. That would be incentives related to promoting green and sustainable construction, carbon credits given to developers for building with wood. There's well over 500 buildings now in England built of CLT. It is catching on in the US and Canada. We have at least 100 projects in the United States, and maybe there's 500 actually in development, some form of design development phase or anticipated construction. About the same time that it became widely used in Europe, the cross-laminated timber made it into the International Building Code, including, that was the 2015 edition of the International Building Code, including the ability to use it in exterior walls of Type 4 construction. Now they did need, since it's not non-combustible and it's not fire retardant treated, it does need to be protected with fire retardant treated wood, gypsum, or other non-combustible material in the exterior walls. A CLT handbook was developed, and the provisions for CLT are now in the AWC National Design Specification, referred to as the NDS. There's a mandatory CLT product standard. It's the APA PRG 320 standard that's referenced in the code. I like this photograph because this is a picture of a test facility, a panel being set, lowered into place on the test structure that was constructed for a series of fire tests performed at the Bureau of Alcohol, Tobacco, and Firearms Fire Research Laboratory. And we like this photograph because it shows the scale of what's going on with these big mass timber panels. This one is about 40 feet long, 8 feet wide, 7 inches thick, and weighs about 3 tons, forming the floor ceiling at the top of the test structure. This, by the way, this panel was later repurposed after the testing for construction of residential buildings by architecture students at Yale. So CLT can be used in either horizontal or vertical applications as walls or as floors. In mass timber buildings, they'll probably used in conjunction with glue laminated timber. Mass timber floors, the staple will be CLT most likely. We'll talk a little bit more about this test facility and this test series. Jason will cover it well later in the program. There's other mass timber products that are going to be part of mass timber building systems. Nail laminated timber is not a new concept. It's in the code currently as mechanically laminated decking or mechanically laminated timber. It's simply made up of dimension lumber that's nailed together face to face. It can be prefabricated, and often is, and shipped to the site, or it can be actually built on site. Most of us are very familiar with glue lams, glued laminated timber. Beams are well established in design and in the code, and so you're familiar with those. They differ from CLT in that all the laid up members, all the layers, the laminated members are oriented in the same direction. So they do have different structural properties, and CLT, again, very different in structural properties from glue lam. But all of a sudden we have a new construction system. It really doesn't fit in the descriptions of light wood frame or traditional heavy timber in the middle. It's the new one right here. So let's do a poll question, and don't overthink this one. This is pretty easy, pretty light. Go ahead, Marcy.
Alrighty. Oh, there we go. Cross-laminated timber is primarily intended for use in which type of construction? Is that light wood frame, post and beam, mass timber, or all of the above? So everybody's gravitating toward two answers, so it's going to be one of those two, I would guess. All right, I've got 80% and 30 seconds. So let's see. So 62% say mass timber, 36% say all of the above. And Paul, what is the real answer?
Well, the answer we were aiming for was mass timber. It's a very general question. However, those of you who answered all the above, I could tell you you're right as well, because you can use cross-laminated timber in these other systems. But the intent of the question was just what's it primarily intended for. So well done, everyone. Back to our outline. With the new system emerging, it was natural that the code and the International Code Council, well, what it would want to address it in their codes. The ad hoc committee was assembled. By the way, this picture here is a nail laminated timber floor on top of glue lams with glue lam columns. So the committee, this was really a significant move for ICC, and actually the code provisions and themselves are rather historic, really, because it's been forever since any new construction types were introduced into the code. But the ICC Board of Directors said, let's explore the science tall wood buildings, investigate their feasibility from a structural and a safety standpoint, and if warranted, let's take action on developing code changes. Let them come from a consensus committee. And in the end, that turned out to be a very good thing. It was a balanced committee. The picture here is not just committee members. These were public meetings, and the committee members are sitting around the tables here. But first of all, ICC wanted to gather experienced building and fire officials, leaders, to guide this committee. Next, designers, architects, engineers, leaders in their field, fire protection experts, whether they be fire protection engineers, noted consultants who had experience or an interest noted experts from around the world, and then representatives of all building materials groups, not just wood, steel, concrete, so forth, and also other construction-related professionals. The meetings were open meetings, and there was a lot of participation by many experts that were not actually on the committee. The chair of the committee, Steve DiGiovanni, appointed 4 work groups, and they were definitions and standards, fire, structural codes. These work groups met together, did some work, came back and presented a total of 82 major issues that should be investigated. Hundreds of smaller issues, hundreds of reports reviewed, and they did identify, first of all, performance objectives for buildings that would exceed the current height limits. In order to begin to contemplate what the code requirements should be, they had to envision how these buildings would behave, and of course fire was one of the primary focuses. No collapse under reasonable scenarios, a complete burnout of fuel without automatic sprinkler protection considered. Sprinklers are always going to be required in high-rise, but the committee said, something goes wrong with the sprinklers, the fire department never shows up, let's see how they behave, see how they perform. So it's a very conservative performance objective at the very start. And then how about radiation to and from adjacent properties? If there were a fire, what would happen? Let's look at that. No unusual fire department access issues. They wanted to make sure that was paid attention to. Egress systems, just like for all buildings, especially high-rise, designed to get the occupants out, plus factor of safety. And then finally, suppression systems must be highly reliable, and we'll see even redundant systems in some cases. All right, this is a question, I'm gonna turn it to Marcy, but before I do, I'm gonna say, person coming back to you is Jason Smart. He is our manager of fire research. If I got the title wrong, Jason, let me know later. He's going to continue on our program after this question. So.
All right, so here we go. Which of the following is not one of the Tallwood Building ad hoc performance objectives? Is that no collapse under reasonable fire scenarios, no unusual fire department access issues, egress systems protect occupants during escape, or occupants are protected without leaving the building initially? All right, I think people were listening, and I've got 30 seconds, so. All right, 77% say D, occupants are protected without leaving the building initially. And Paul, what do you say, is that right?
Well, that's right, and I think Jason will concur.
All right,
that's
and
the one that's not one of the performance objectives, right?
Cool. So here I'm switching over to Jason.
Okay, thank you, Marcy.
Mm-hmm.
Can you let me know if you can see the my screen now? I'm on the that polling question we just did.
I got it, Jason. I think you're on.
Okay, great. Sounds good. All right, so yes, that's good. I'm glad most people got that right, because obviously occupants should evacuate the building as soon as they're notified of a fire within the building. So that's not one of the design objectives that the TWB ad hoc committee had identified for tall mass timber buildings. So just to pick up from where Paul left off, I'm first going to describe some of the testing and research that the ICC TWB ad hoc committee considered when developing the mass timber code provisions. Early on, the TWB recognized that it would undoubtedly need testing to validate its proposals. The fire work group, which is a subset of that committee, it's one of those 4 work groups that Paul just mentioned a few slides back. They developed test scenarios, including the physical layout of the test structure, the configurations, and the fuel load. test structure represented a multi-story condominium or apartment building in which each unit had interior dimensions of 30 feet by 30 feet. So it was basically a square, but there were multiple rooms within each apartment. And we'll show you a floor plan in a minute. There was also a corridor and a stair shaft within the test structure at each level. The fuel load is based on a North American study of fuel loading for residential use groups. In fact, to ensure rigorous test conditions, furnishings and other combustible contents were added to achieve a fuel load that was equivalent to the mean plus 1 standard deviation. So the actual fuel load used within the test structure corresponded to approximately the 85th percentile of residential fuel loads when compared to that survey. The expressed purpose of the test series was to evaluate occupant egress tenability, firefighter attack tenability, also to assess systems response to fire, such as the sprinkler systems and other systems within the like fire penetration fire stops and so on and so forth. And then, of course, most importantly, to guide code development. The series, which consisted of 5 separate fire tests, was conducted at the ATF Fire Research Laboratory, and it was supervised by Forest Products Laboratory staff and administered by the Forest Products Laboratory staff. The photo on this slide here on the lower right shows the CLT test structure in which these fire tests were performed. It was all 5 of the tests were performed in the same test structure. Of course, there were some rehabilitations that were performed between each test in order to repair any damage to such as the non-combustible protection and so on and so forth. But yeah, all 5 of the tests were performed in this same structure. By the way, that's the same structure that Paul showed a photo of as an example of how big CLT panels can be. So this is the apartment or condo floor plan that was selected by the fire work group for the 5 tests. There was one 900 square foot apartment on each level of the test structure with a corridor leading to a stair shaft on each level. So you can see that these fire tests were truly full scale. It was a full-size apartment or condo on each level. The TWB Ad Hoc Committee insisted that the construction must be compliant with the current IBC, as well as with all of the proposed code changes that were being developed simultaneously. To achieve this, 20-minute rated entry doors were installed on the apartments, and 90-minute doors were used on the stair shaft to separate the stair shaft from the corridors. The corridor was instrumented to determine firefighter tenability and occupant egress tenability within this egress route. So the scenario represented by the first 3 tests was a highly unlikely one in which you have basically an unlikely overlap of 2 scenarios. The first part being that the automatic sprinklers fail to activate, and then the second part simultaneously being that the fire service does not respond at all to suppress the fire throughout the entire duration of the fire. So basically, we're looking at the realm of where those 2 scenarios overlap, which makes it even less likely. In test 4, the automatic sprinklers were allowed to activate on their own. So this represented a typical scenario, since these tall mass timber buildings are required to have sprinklers. Notice I said tall mass timber buildings are required to have sprinklers. Obviously, as Paul will show later on, there are cases where mass timber buildings can be designed without sprinklers. However, they can't be tall then. They're limited to very low, relatively low heights then. So all tall mass timber buildings will have sprinklers. And then test 5 was an unusual test condition. I'll get to that one on the next slide. And of course, what I'm talking about here is all dealing with the TWB work product and the prescriptive provisions that they developed. They're going to go into the 2021 IBC. I'm not talking about any potential performance-based designs or alternate means and methods or anything like that. So this is the test matrix for the individual tests within this series. Test 1 served as a baseline to establish the performance of fully protected mass timber. This fully protected configuration represents type 4A construction. And that's what they had envisioned at that point as type 4A. It became known as that later on, actually. But at any rate, that's type test 1 is equivalent to what's now recognized as type 4A. And then test 2 was an investigation of partially exposed mass timber on the ceiling, representing maximum allowable exposure in type 4B construction. Test 3 was an investigation of exposed mass timber on the walls, again representing the maximum area exposed allowed in type 4B. So test 2 and 3 were type 4 or representative of type 4B. Like I said a minute ago, test 4 looked at sprinkler effectiveness in mass timber construction. It was the shortest lived test. Within about 6 minutes, the sprinklers had effectively extinguished the fire. Test 5 was an investigation of the ability of a manually charged sprinkler system, which is initially incapacitated for some reason, to help control the fully developed fire. In order to simulate this scenario, the water supply to the sprinkler system was initially shut off, and then it was manually charged 23 minutes after the fire started. This simulated a scenario in which the fire service hooks up a water line at the fire department connection upon their arrival at the scene. All 5 of these tests were performed in the same test structure. The first 3 tests were carried out for 3 and 4 hours and until the fires had effectively burned out due to lack of remaining combustible contents. The other 2 tests, tests 4 and 5, were much shorter because the sprinklers suppressed the fires before the contents could be consumed. A good portion of the fuel load was achieved through a combination of the typical residential furnishings. You can see them in these pictures here. Combustible floor coverings, which you can see here. OSB was used just because it's cheaper, but that actually has a higher fuel load than a lot of typical combustible fuel coverings anyway, or floor coverings anyway. And then cabinetry, which you can see back in the kitchen there, and other combustible contents. Even with all of these furnishings and contents, it was still necessary to add additional fuel load in order to achieve the relatively high TWB specified fuel load. As I mentioned earlier, the specified fuel load was 1 standard deviation higher or above average for Group R occupancies. So in order to get up to this required level of fuel load, wood cribs were also added to the test structure for each test. And the fuel load was the same for all 5 tests. So you can see there's a wood crib that was placed on the coffee table, a wood crib placed on this this piece of furniture right here. There were quite a few wood cribs you can't actually see because they're in the background, and also in the bedroom there were quite a few. There's some furnishings in the bedroom that that you can't see because of the angle of this photo on the right here. There was a desk and a chair there, and a couple of pieces of furniture on either side of the desk as well. So this doesn't show all of it, but it shows the majority of the combustible contents. These still shot photos of test 1 show conditions at key stages during the fire growth and decay phase. By the way, the term decay phase simply refers to the stage in which the fire intensity is diminishing due to a reduction in available contents, namely because most of those combustible contents have already been consumed at this point. So that's why the fire is decreasing in intensity during the decay phase. The photo in the upper left shows what it looked like shortly after ignition. The living room reached flashover at about 12.5 minutes after ignition, and the bedroom reached flashover at about 17 minutes. The peak heat release rate of this fire was more than 20 megawatts, and that was the case for all 3 of the first 3 tests, which were allowed to burn unhindered and which were supplied with enough combustion air. As I mentioned, it was allowed to burn without intervention or automatic suppression. So this was the case with all three of the first three tests. The bottom center and bottom right photos show the condition of the living room and bedroom following the test. Note that all of the combustible contents and the unrated partitions are gone. You can barely see the unrated partitions on this. There'll be better photos showing the unrated partition later on. But the mass timber structural elements are essentially unaffected. The mass timber elements also did not become involved or contribute to the fire. In test 2, 30% of the CLT ceiling areas in both the living room and the bedroom were left exposed. This amounted to 20% of the overall ceiling area or overall floor area of the total apartment. And again, that's the well, we'll talk about. I'll show a slide that actually has an excerpt later on of the language, the code language, which specifies these exposed area limits. But 20% is the limit for the ceiling area. So this basically maxed out the allowable exposed ceiling area for Type 4B. And that's shown in these two photos here. You can see that exposed area. This is just in the living room. There is an equal area exposed also on the ceiling in the bedroom. And then the photo on the left here shows water barrels that were placed on the roof of the test structure on top of the floor ceiling assembly in order to load that assembly during the test. I didn't show a video of fire test 1 because we only have time to show one brief video here in this presentation. So I chose to show fire test 2 because this one has some exposed areas, again, on the ceiling. You can see in a few of these panes the exposed areas. And then in these panes down here, you can see the men that are in firefighting apparel igniting the fire. And you can see it was ignited in the lower kitchen cabinet. Same place it was ignited the same way and in the same place for each of the 5 tests for repeatability purposes. And I'm going to go ahead and fast forward here a little bit until you'll see it spreading, especially as I fast forward here. And it's spreading onto the combustible floor covering there. And then I'll fast forward to flashover, which, as I said, occurred at about 12 and a half minutes. And that's right about here. So there's flashover of the, notice flashover has only occurred now in the left portion there. That's where the living room and kitchen are. Again, the ignition was in the kitchen cabinet, so that makes sense. And then if you look over here in this pane, this is a shot of the bedroom, same with this. And you can see the flames and smoke starting to come into the bedroom. The bedroom door was left open, as were all of the interior doors, in order to allow for the fire to spread unhindered. However, the self-closing 20-minute rated door, entry door into each of the apartments was left closed for each of these tests, except for one test, which I'll explain later. But for each of these first 3 tests, that self-closing door was left closed because it would be closed since it's self-closing. Now we're approaching flashover in the bedroom, which occurred about 5 minutes, or yeah, about 4.5 or 5 minutes after flashover occurred in the living room and kitchen. And that's it just occurred there. You saw the bed start to flash there. And in this screen, you can see the plumes coming out of both openings now, both from the bedroom and from the living room and kitchen. So this is what they'd call the fully developed phase here. This is a fully developed fire throughout the entire floor plan of the apartment. Now I'm going to fast forward, and as the combustible contents are consumed, you can see the intensity of the fire diminishing. This is the decay phase that I referred to earlier. And for the latter half of the test, it continues to decrease in intensity. until at about 4 hours. This test was carried out to 4 hours just to make sure that there were no flare-ups or fire regrowth or anything like that, and there wasn't. And so it had pretty much self-extinguished. You can see a little bit of smoldering over here in the bedroom at the end of the 4 hours. That was just some remaining combustible contents. I think they were books from books that were put into a bookshelf there in the bedroom. Here are the still shots of some of the key events during and after test 2. The living room reached flashover at about 12.5 minutes, like I said, and then the bedroom was about 17 minutes, reached flashover at about 17 minutes. The fire was allowed to proceed for 4 hours, by which time the exposed mass timber had already self-extinguished. Notice that the protective layer of char had formed on the exposed portions of the mass timber ceiling. You can see that both on the living room ceiling and the bedroom ceiling here in these two lower right photos. Here's a post-test photo that was taken after the gypsum was removed from the ceiling after test 2. In this photo, you can see not only the post-fire condition of the CLT, but also that of the glulam columns and beams. The areas protected with gypsum wallboard were uncharred, with the exception of minor localized surface charring at the lower edges of the glulam beam. You can see that here. The exposed area of the ceiling can be seen here as the charred rectangular area to the upper right of the man on the yellow ladder there. And this photo shows a sample cross-section which was cut out of the exposed portion of the CLT ceiling following test 2. On this sample, the char has been scraped off in order to more clearly show the depth of the char. As you can see, the char was not quite 1 lamination thick. So these laminations were 1 3/8 inch thick. So that means this char depth was between 1 and 1 1/4 inches here. And the reason a portion of the lower lamination was not charred, this part right here, is because this portion of the CLT ceiling was protected. It was protected by either the gypsum wallboard or the trim work that formed the border between the protected areas and the unprotected areas. So this is good. This is a good cross-section because it actually shows the transition between the protected areas and the unprotected areas following the fire. In test number 3, wall B was exposed in the living room and wall D was exposed in the bedroom. This layout shows the location of these exposed walls. Notice I say the wall D was exposed in the bedroom and wall B was exposed in the living room. I say that, I qualify it by saying in the bedroom and in the living room because the exposed portions of walls D and B went from approximately here to about right here. The walls were not exposed in the bathroom or in the kitchen. So, and then same with wall B, the exposed portion went from about right here where the living room starts to where it intersects wall A. That amounted to about 40% of the total wall area. The center wall separating the bedroom from the living room was light gauge steel. It was constructed with light gauge steel infill between the glulam columns, and it had 1/2 inch unrated gypsum board on each side. This wall didn't need to be fire resistance rated because the loads were carried by the glulam columns and beam, which were fire resistance rated. So as expected, the center wall quickly disappeared during the fire test, leaving only the mass timber walls and columns and beams. And of course, they still retain their load carrying ability. In test 3, where about 40% of the CLT walls were exposed, flashover times were about the same as in the first 2 tests. Again, the fire was allowed to progress without intervention all the way to burnout. And unfortunately, The last photo here we have from test 3 doesn't show the very end of the test. This shows about halfway through the fire test, and you can still see some burning there because there were still some combustible contents left. In test 4, all of the mass timber surfaces were exposed in the bedroom and living room, and the automatic sprinkler system was allowed to activate normally, which it did at about 2.5 minutes after ignition. Within 6 minutes, the fire was effectively extinguished by the sprinkler system. It probably would have been extinguished even sooner if it weren't for the fact that the cabinet shielded the fire from direct sprinkler impingement. Remember that the ignition point was under the cabinet, under the lower kitchen cabinet in each of these tests. But the fire didn't spread beyond the lower kitchen cabinet, and this is the sum total of the damage that occurred in test 4. Just like for test 4, in test 5, all mass timber surfaces were fully exposed in both the bedroom and the living room. The sprinklers were purposefully prevented from discharging in test 5, though, and then they were manually charged 20 minutes after the time at which the sprinklers automatically activated in test 4. This simulated a scenario in which the sprinklers fail to activate automatically, but are then manually charged by the fire department connection, or at the fire department connection by the fire service upon their arrival at the scene. Flashover conditions were reached in the kitchen, and the bedroom was very near reaching flashover, although it didn't quite reach flashover, but it was definitely reached in the kitchen. Within 7 minutes of manual charging of the sprinklers, the fire went from a fully developed fire, which can be seen here in the upper photo, to being effectively suppressed, as you can see in this lower photo here. So that was just a 7-minute period between that and that. As you can see in this summary table for all 5 of the ATF tests, flashover in the living room was fairly consistent at around 12 or 13 minutes after ignition. And the time to flashover in the bedroom for all 3 of the first 3 tests was also even more consistent, actually, at about 17 to 17.5 minutes. And this is despite the differences in exposed mass timber areas between these first 3 tests. The time that it took for flames to breach the 20-minute rated door into the hallway was about 27 minutes in test 1 and 30 minutes or 31 minutes in test 2. In test 3, the flaming on the backside of the door of the 20-minute rated door occurred early because the door was not installed correctly. But in any event, the flames did not spread beyond the door within the corridor, and that's evident in the videos of all 3 of these first 3 tests. The Research Institute of Sweden, or RISE, R-I-S-E, used their model to predict the behavior of ATF tests 1 through 3 before they were even performed. The measured data from the actual fire test closely matched predicted values. For example, in this graph, the solid black line is the predicted rate of heat release rate for test 2, and and then the blue line is the plot of data collected at ATF for this same test, for test 2. Based on this, it was concluded that it is possible to accurately model the fire performance of mass timber structures. The full report that details the results of this test series was published by the U.S. Forest Products Laboratory in 2018, and it's available on their website at this address here, or you can just go onto the FPL website and just do a search for GTR 247. All of the tests and videos were recorded also, and these videos are also available for free public viewing, either at regular speed or the time-lapse versions like the one that we watched of test 2. These time-lapse versions are available on the AWC, the link, you can get to them through a link on the AWC webpage, specifically the Tall Mass Timber webpage on the AWC website. So now let's move on to the TWB work product and the resulting new code provisions. The committee decided to approach their work by first defining new types of construction, as Paul alluded to. The proposed new types of construction are created in existing section 602.4 of the IBC. The TWB committee developed a total of 14 code change proposals under the 2018 Group A cycle. 4 of these code change proposals address the new types of construction and height in feet, height in stories, and allowable area. And then the remaining 10 proposals include 3 correlating items and 7 proposals introducing various new fire safety items for tall wood, all of which either I will touch upon or Paul will talk about later in this presentation. All 14 of these proposals were approved as recommended and will be included within the 2021 I-codes. Additionally, though, the TWB developed 3 other code change proposals that are currently being considered under the Group B cycle. Paul is going to talk more about those also. The TWB committee found it necessary to develop a couple of new definitions for new terms for inclusion within Chapter 2 of the IBC. Specifically, these are mass timber and non-combustible protection for mass timber. The definition for mass timber is based on the same minimum cross-sectional dimensions that apply to traditional heavy timber. It should be noted that a code change in the last cycle for the 2018 IBC moved those dimensions and other related information back into Chapter 23, which deals with wood construction. It was also necessary to develop a definition for the term non-combustible protection because this term is now used pretty extensively in the new provisions that detail mass timber construction. It applies specifically to mass timber construction, and it is different from other forms of fire protection. Non-combustible protection is designed to increase the fire resistance rating of the mass timber to which it is applied, and also to delay the combustion of that mass timber. We'll talk more about this a little later. Moving on to the meat of the new provisions, let's talk about the new mass timber construction types and the various prescriptive requirements associated with them. 3 new types of construction are described here. They are designated as types 4A, B, and C. Let's look at them each individually now. And by the way, I wanted to point out these icons here for ease of understanding. On the next several slides, anything that only applies to type 4A, if what I'm talking about only applies to type 4A, then it'll have just this blue icon. If it only applies to type 4B, it'll only have this this green icon, and then likewise type 4C will have this icon. If it applies to all 4, then you'll see, or all 3, then you'll see all 3. The TWB began by acknowledging that fully protected mass timber performed like type 1A construction from a fire standpoint. Thus, they chose to call that fully protected condition type 4A to make it analogous. And in keeping with this analogy, type 4A also requires the fire resistance ratings that are the same as those required for type 1A. But an additional requirement for type 4A that doesn't apply to type 1A is that no less than 2/3 of that fire resistance must come from non-combustible protection. We'll talk about what non-combustible protection is. I kind of went through the definition, but we'll get into more details on exactly what that means later on. Because the mass timber elements will be fairly large for structural purposes, they also have inherently a significant degree of fire resistance even without the non-combustible protection. This fact has been recognized of heavy timber construction for over 100 years. It should be noted that because of the height limitations for types 4B and 4C, which are more strict than that for type 4A, the taller buildings, and by taller here I'm referring to between 12 and 18 stories, they'll only be permitted prescriptively under type 4A, which doesn't allow any exposed mass timber. So really the tall mass timber buildings, the ones higher than 12 stories, will not have any exposed mass timber if built prescriptively. A similar correlation was drawn to type 1B. So the partially protected condition was called type 4B, to continue with that analogy. Type 4B is like type 4A, except that non-combustible protection may be omitted in certain locations. And we'll talk more about the limitations on those permitted omissions. And of course, as I just mentioned, the height limitations for type 4B are more restrictive than for type 4A. From a fire safety standpoint, these height and area limits counterbalance the fact that you can have mass timber surfaces exposed in certain limited areas in type 4B. The new code provisions place specific limits on how much area of the mass timber can be exposed on various surfaces, and also how close those areas can be to one another. Type 4C requires non-combustible protection only in certain locations, such as concealed spaces, stair shafts, and exterior walls, or the outside face of exterior walls. That said, it is still required to achieve the fire resistance ratings of tables 601 and 602 by its own characteristics, meaning the inherent fire resistance of the mass timber itself. In exposed areas, fire resistance is primarily achieved by additional wood cover that is above and beyond that which is required to carry the structural load. These fire resistance ratings are the same as those that are required of types 1B and 4B, which we'll look at now. This is the table 601 from the IBC, as now modified for the 2021 IBC. It specifies minimum fire resistance rating requirements for various building elements across all of the construction types. The new columns for the three new construction types are identified here under the heading Type 4. There's A, B, and C. Notice that the fire resistance rating requirements of Type 4A, right here in this column, are identical to those in Type 1A, which I alluded to earlier. These two columns, if you compare the columns that are identified by the elongated blue oval, you'll see that they're identical. And then likewise, both 4B and 4C have exactly the same fire resistance ratings as Type 1B. And these columns are highlighted in light blue. As for the existing Type 4 construction using heavy timber, the TWB committee made a decision not to make any changes to this construction type. That is, other than to change the designation to add the -HT to the end of it in order to better distinguish it from the new Type 4 construction types. This type of construction has existed for many decades. I'm talking about Type 4 HT now. And so the committee just decided to leave well enough alone here. One of the reasons I point this out is because I want to stress that the new mass timber construction types 4A, B, and C, are not the same as Type 4 HT. There are some significant differences between them, and we'll talk about those unique aspects for the new mass timber types of construction in the next few slides. Some of the key fire performance features that have been built into the new provisions for types 4A through 4C construction are listed on this slide. For example, the new IBC provisions require that mass timber elements must be protected with non-combustible protection as specified in section 602.4, and there are some limits, like I said, we'll get into those specifically for types 4B and 4C. Structural elements are required to have fire resistance ratings as shown in table 601, which I showed you an excerpt of a few slides back, and table 602, which deals with fire resistance from the exterior side of exterior walls. And the adhesives used in mass timber are required to be qualified through a series of both small-scale and large-scale fire tests. This is to ensure that they do not undergo heat delamination, which could lead to fire regrowth. And then also, no combustible light frame members are allowed anywhere in the buildings. You may have seen in some of the pictures I showed already of the ATF test structure, and I think I have a better picture coming up a little bit later, showing that steel studs were used for the non-load bearing interior partitions and infill. In fact, no combustibles are allowed in any of the concealed spaces, except for materials that are currently allowed in plenums by the International Mechanical Code and NFPA 13. An example of this would be insulated wires, so that they would be allowed, but no combustibles such as light frame wood or anything like that in the concealed spaces. Here's an excerpt from section 602.4, which applies to all three of the new construction types. At the top of this excerpt, you can see the provision requiring CLT to be qualified in accordance with PRG 32018. PRG 32018, by the way, PRG 320 is the material standard that is referenced in the IBC for CLT. So any CLT used prescriptively under the IBC is required to comply with PRG 320. And specifically, the 2018 version is what's going to be referenced for CLT used under the 2021 IBC, which is where this provision is going. As you can see from the strike through and underline here in this slide, this paragraph was modified through a floor mod at the code hearings. This modification was considered acceptable because the 2018 version of PRG 320 included adhesive qualification tests to prohibit heat delaminating adhesives. So it actually provides a more comprehensive and robust means of addressing the issue than the previously proposed language did. And it effectively prohibits use of adhesives which can undergo heat delamination, leading to the type of fire regrowth that the committee was concerned with, the TWB committee. Regarding shafts, elevator hoistways, and the like, in buildings up to 12 stories, interior exits, elevator hoistways, and shafts are permitted to be constructed of mass timber elements. However, those mass timber elements are required to be protected with non-combustible protection. And then in buildings taller than 12 stories, interior exits and elevator hoistways are required to be constructed of non-combustible materials. An example of this can be seen in the 18-story Brock Commons building in British Columbia, which Paul showed on the first slide of this presentation, and he talked a little bit about. It has reinforced concrete shafts. In all three of the new construction types, everything outboard of the mass timber and the exterior walls is required to be non-combustible, except for a WRB, a water-resistive barrier, which is required to meet certain fire performance thresholds. Also, mass timber walls are required to have at least one layer of 5/8" type X gypsum board or equivalent non-combustible protection on the outside. I'll note that on top of that, additional non-combustible protection is required where Table 602 stipulates a fire resistance rating of greater than 1 hour. So if Table 602 says you have to have greater than 1 hour fire resistance rating from the exterior side on exterior walls, then you'll actually need more than just one layer of 5/8" type X on that exterior side or exterior face of the mass timber in the exterior walls. And that applies to all three of these new construction types, including type 4C. And of course, it's not explicitly called out in this diagram, but the interior side of exterior walls are also required to meet the fire resistance ratings that are stipulated by Table 601. I mentioned a few slides back that no combustibles are allowed in any concealed spaces. Because of this requirement, mass timber surfaces which bound concealed spaces, such as this right here, there's actually mass timber behind this gypsum here, they're required to be covered with non-combustible protection. And any framing that's used within this concealed space, such as this framing here, must be non-combustible. So in this case, these are photos from the ATF test structure. This was a drop ceiling here forming a concealed space. Obviously, steel studs had to be used, or some sort of non-combustible framing had to be used, so steel studs were used. Let's see, so you can see that both of these are from the ATF test structure. And again, this requirement also applies to all three of the new construction types, including type C, type 4C. So now let's take a look at some of the other provisions that are specific to just one or two of the new construction types rather than all three. First, we'll talk about those that are specific to type 4A. All mass timber surfaces in type 4A are required to be protected with non-combustible protection. There's no exceptions in type 4A. And that non-combustible protection has to be sufficient to provide at least 2/3 of the required fire resistance rating. You can never have less than 2 layers of 5/8" type X gypsum on interior surfaces, or the equivalent thereof, equivalent non-combustible protection to 2 layers of 5/8" type X. Also, mass timber floors must have a minimum 1-inch thick non-combustible topping. Typical examples of this 1-inch thick non-combustible topping would include cast-in-place concrete or gypsum concrete. This, by the way, this requirement for the 1-inch non-combustible material over the mass timber floor doesn't just apply to 1A, it also applies to 1B. So, and then just as in type 4A, I'm sorry, I said 1A before, I meant 4A and 4B. Just as in type 4A, mass timber surfaces in type 4B construction are also required to have non-combustible protection providing 2/3 of the fire resistance rating. However, there are exceptions in type 4B. I mentioned earlier that one of the things that distinguishes type 4B from type 4A construction is that limited areas of exposed mass timber are allowed on the ceilings in type 4B. Here's the code section which details exactly what these limits are. This section says you can either have either 20% of the floor area exposed on the ceiling, or 40% of the floor area exposed on the walls, or you can have some combination of both of these. But there's a limit, and I'll get to the equation that shows exactly what that limit is in just a minute. But first, let me show that there's a fourth exception that can apply simultaneously with either of these first three. And that is that mass timber columns and beams, which are not an integral part of walls or ceilings, are allowed to be left unprotected. And that applies, of course, to 4B, type 4B. The TWB committee felt that this was justifiable because typically the total surface area of standalone columns and standalone beams is relatively small compared to the area of walls and ceilings. For cases in which there is a combination of exposed areas on both the wall and ceiling, this is the equation that I alluded to just a minute ago. This is what limits the total exposed area on the combination of both the walls and the ceilings. It's simply a sum of the two ratios of actual exposed area to allowable exposed area on the ceiling and then on the wall, respectively. And that summation must be less than or equal to 1.0. And this equation is modeled after the separated mixed use provisions that exist currently in the code. Also, if the combination wall ceiling exposure option is used, the exposed portions of walls and ceilings must be at least 15 feet, separated by at least 15 feet from one another. This minimum 15-foot distance is measured horizontally between the exposed areas of mass timber. Obviously, this is intended to reduce the amount of potential radiative heat flux that one area might receive from another in the event of a fire. And then lastly, there's type 4C. Type 4C is sometimes described as a mass timber construction type in which all of the mass timber surfaces are unprotected. However, I like to point out, though, that this is actually an incorrect generalization. Non-combustible protection is actually required in numerous locations within type 4C construction. And these include, as I kind of touched upon earlier, the outside surfaces of mass timber and exterior walls, and then also mass timber surfaces within concealed spaces, and also both the inside and outside surfaces of mass timber within shafts. Also, while non-combustible toppings are not required for mass timber floors in type 4C like they are in types 4A and 4B, there is a requirement that floors in type 4C are required to meet the provisions of IBC section 804. This section applies, of course, generally to other types of construction as well. So with that, it's been a while since we've had a polling question. I'll hand it back to you, Marcy, to ask this one.
Sure thing. So which of the following are proposed new types of construction? Is that 4A, 4B, and 4C? Or is it 4 heavy timber? Or 1 heavy timber, 2 heavy timber, and 3 heavy timber? Or all of the above? I think people, let's see. All are gravitating toward one answer, so hopefully that's the right answer. And I've got about 35 seconds or so, so let's share the answers. Excuse me, 77% say A, 4A, 4B, and 4C. What do you say, Jason?
Yep, that's correct. So the majority got it right. Those are the new types of construction, types 4A, 4B, and 4C. Type 4-HT, as I mentioned earlier, is not a new type of construction. That's been around for a long time. Only the designation has changed. So.
Okay,
yep.
And then I'm going to switch over to Paul to continue out the presentation.
Okay, thanks, Marcy. Great job, Jason. Let's get off that screen. So we have some additional fire safety features we want to talk about for the new mass timber construction. And I want to emphasize one of the principles here, and that is, this is a new principle. It only applies to mass timber in the code. We're all used to tested assemblies that achieve fire resistance. We're used to calculating fire resistance of exposed mass timber or exposed heavy timber elements. But this principle, this is the code text, and Jason explained this. I just want to reemphasize. The fire resistance rating of mass timber elements consists of the fire resistance of the unprotected element added to the protection time of the non-combustible protection. So for instance, if the floor is a 2-hour floor, right here, there may be some inherent fire resistance or designed fire resistance in the exposed floor. You can add that to what's provided with the gypsum to get the total fire resistance. There's 2 ways to do this, by the way. So the question is, how do we determine the amount of fire resistance provided by the non-combustible protection? One way to do that is by testing. You set up a test program where you're testing the unprotected element, like the unprotected CLT floor, and you test it to failure by ASTM E119 or UL 263. Take the same element, protect it with non-combustibles, test it again. The difference in fire resistance rating time to failure, that's the amount of contribution the non-combustible protection is providing. The general principle, as we said, is it must provide at least 2/3 of the overall required rating of the element. There's also a prescriptive option for achieving this. So in Chapter 7, you'll see 2 new tables. Fire resistance rating of the element over here, required contribution from the non-combustible protection in minutes over here. You want to know how many minutes you get with these types of gypsum wallboard? Here they are. Right. Remember, this also applies to type 4C because there are certain elements in type 4C that do need to be protected, such as exit shafts. Attaching the gypsum, the code will contain requirements for specific attachment of the gypsum. They do have to be staggered layers, offset layers, a stair-step profile at wall to ceiling and wall to wall intersections. Primarily important wall to ceiling, where the gypsum ceiling is resting on the wall ceiling at each layer. All right. Super tall buildings currently in the IBC, when they get to 420 feet, their sprinkler systems have to have a redundant, in other words, 2 separate water supplies. This requirement was chosen to kick in at 120 feet for tall mass timber buildings. Another requirement, 703.9, you'll find sealing of adjacent mass timber elements. So a mastic or a caulk or an adhesive in between mass timber elements where they join. This is not for any quantifiable fire resistance. This is to prevent air movement, to prevent smoke movement throughout the building in the case of a fire. And then finally, this non-combustible protection on mass timber elements is very important. So what if someone who's using the building decides to remove it? The committee said, let's put a provision in the fire code that requires owners to document their maintenance of the non-combustible protection on the mass timber, so that they have a record of it if something is damaged or removed and a fire official makes an inspection of the building. They're going to be able to receive from the owner, and it is a responsibility of the owner to maintain the fire resistance. They're going to be able to ask for that documentation, inspect any areas that perhaps were damaged or not protected. How about during construction? Construction fires are a very serious matter. We do have a construction fire safety coalition. You can find that information on our website. For mass timber buildings, it will also be important. All the typical requirements for fire safety during construction in Chapter 33 of the IBC and the IFC will apply. Standpipes when the building reaches 40 feet, water supply for fire department operations, access to the site, even fire watches at the order of the fire official. It's not listed here. These will all kick in as is currently required. But in addition, as mass timber buildings go up, we're going to require, the provisions are going to require that the protection begin as the building go up. So the idea here is we don't want a lot of exposed mass timber at a very vulnerable stage of construction. As we get taller, as we get up beyond 4 stories above what's protected, before we go higher, we're going to have to protect the story that's more than, the first story that's more than 4 stories below the floor of active construction. So if this is the 9th story, before construction begins at that, you have to protect this story here, which would be the 4th story, and then you can move up. This is simply 1 layer of gypsum that's required as an initial deterrent against ignition, even if there's more gypsum required to be installed later. You have prescriptive fastening for the exterior, the required exterior non-combustible protection of 40 minutes. Just so you know that's in there. I'd like to talk now about 3 particular changes that Jason mentioned. They're happening in this code change cycle, Group B. The first one has to do with connection protection. The heading of this section, new section as it stands right now, says connection fire resistance rating. However, as we all know, there's no standard in the code currently for the testing of connections and their fire resistance. What this is talking about, if you're familiar with current heavy timber design and when heavy timber construction is required to be fire resistance rated. It's not always required to be fire resistance rated, but when it is, the connectors between rated elements have to be protected with materials that equal the same fire resistance as the connected elements. That same principle will be carried through with this provision that's been approved by the committee, Code Development Committee, and will be up for a vote and is anticipated will get approval because it has good consensus in the fall. The trigger here, or the goal or the focus, is the temperature rise on the connector itself, but the principle is the same. You will be protecting the connections or the connectors with materials that equal the fire resistance rating of the connected elements of what their required rating is. You have a good resource now. Technical report number 10 has been revised to include all provisions for CLT, including the protection of connections and connectors. So there'll be some design, there are some design examples in here, and you can download this off our website. Among the Group B proposals are the requirement to inspect that cover for connections back in Chapter 1. And there will be special inspections required for mass timber construction. They will be listed in a table, if this is approved, we're assuming it will be, in Chapter 17. You can take a look at that. In the current monograph, you can find the committee reasons for that. I'm going to go back to a poll question now. Marcy?
Yep. So we're going to fly through these real quick, but in types 4A and 4B, what minimum contribution must be made by non-combustible protection? Is that half of the required fire resistance rating of the building element, 2/3 of the required fire resistance rating of the building element, 3/4 of the required fire resistance rating of the building element, or none of the above? All right, I've got 30 seconds. I'm going to go ahead and close. All right, 61% say 2/3 of the required fire resistance rating of the building element. What do you say, Paul?
They're correct.
Excellent.
So the principle is required rating of the element, 2/3 of it has to be provided, at least 2/3 have to be provided by the fire resistance, or by the covering, not combustible covering. All right, finally, let's talk about building sizes. There are restrictions, of course. They are increased over conventional frame construction. They're not as much as type 1A, for instance, but this is height in feet. Just a little excerpt of the table, just showing you an example. Say Group B, type 4A, 270 feet, type 4B, 180 feet, which is parallel to the type 1AB. The committee chose not to make the height unlimited for type 4A, and 4C is the same height as is currently required for heavy timber, regular heavy timber. And by the way, I'll go back up to that for a moment. These rows over here are non-sprinklered and sprinklered, but at high-rise heights, they're always required to be sprinklered, and even at low-rise, Group R is required to be sprinklered. About height in stories, here's the top one, B, 18. It's the same as for Group R. That's for type 4A, 12 stories, 9 stories. This is just showing Group B in the top of the table here. You can see that it's reduced for certain occupancies. The committee used some judgment about this based on relative risk and function of the building. And for Group R, that 9 turns into an 8 for Group R. Allowable areas are increased, but they're not unlimited areas, and as in accordance with type 1. They're comparable to type 4 HT with a factor. Factor is considerable when you get over here with the high protection of type 4A. But I'll remind you that taking this row here, sprinklered multi-story, it's the most applicable row. The area of the entire building cannot exceed 3 times the allowable floor area for a single story in a multi-story building. So you get to multiply that by 3, And then you have to spread that total building area out among all the stories you have above. So as you go higher, your floor areas will get smaller. Here's a summary slide about 4A. I think these are helpful. Most use group, or many use groups, maximum height 270. Not all, certainly not H, not E, and some of the others. Not I, certainly. 9 to 18 stories, fully exposed mass timber, fully protected. Sprinklers, yes. Primary structural frame, 3 hours, 2-hour floors. Here we go. Fire resistance rating from the non-combustible protection, 120 minutes on the primary frame. Stair towers must be non-combustible. Jason mentioned that, and then can have concealed spaces, but they have to be protected. Let's take a look at type 4B. 180 tops out, depending on the occupancy, 6 to 12 stories. You can definitely have some exposed mass timber, which is a nice feature. Sprinklers, yes, 2 hours, 2 hours, 80 minutes. Protected mass timber is permitted for the stair towers. Again, this is only up to 12 stories, 180 feet. Beyond that, you have non-combustible stair towers. And concealed spaces, okay, if protected and so forth. Type 4C, this corresponds to the current height limit for a sprinklered heavy timber building as it stands in the code right now. Stories could be increased over what's permitted in the code though right now. Mass timber can be fully exposed, but of course, not in the concealed spaces, not for the stair towers, not for other shafts through the building. Those do have to be protected. Still have the high type 4B ratings, 2 hours, and so forth. Nice schematic that compares these. The total building areas here are listed below here. Again, this total building area would have to be spread out between all these floors. This is not a single story area, it's a building area. And you have to divide that by 18 to get the allowable floor area in that case. This is current heavy timber here. So you have those total building areas that might be helpful. And if you want to go back and actually read the text of the code changes, type A, Group A cycle, here they're listed and their numbers. You can find it on the ICC website in the monographs. And I think we have another poll question. Let's see.
One more, and this is the last one. So for certain occupancies, which is true regarding maximum height and number of stories for proposed types of construction. So is that type 4A can be 270 feet and 18 stories. Type 4B can be 180 feet and 12 stories. Type 4C can be 85 feet and 9 stories, or all of the above. All right, and so if we have time for question and answer, I'm going to close this. And so 87% say all of the above. And are they right?
They're right.
Excellent.
Well done. I think we're going to turn it over to Buddy Showalter. Buddy?
Okay, Paul and Jason, thank you both very much. There's a question about the ATF tests and just the fact that those were fairly open, ventilated test structures. Was that on purpose? Is that representative? Talk a little bit about kind of that whole test setup.
Sure, yeah, I'd be happy to. Yeah, the TWB committee made the decision to have that size opening because it basically represents a case where you have a curtain wall on one whole side of the building. In fact, I guess in a lot of cases, you might actually have curtain walls on more than just that one side. But for the purposes of data collection and also making sure that all of the entire plume went up into the hood in the test lab, it was necessary to keep all of the openings on just one wall. Typically, there would be a glazed curtain wall on a building like that. In fact, in tests 4 and 5, there was a glazed curtain wall installed on those openings, and you could see the effects basically that stifled growth of the fire because of lack of oxygen. And so the TWB committee wanted to ensure that the fire had a chance to get going and that it would reach flashover, and so they opted not to put glazing on that wall, on wall A, over those openings, in order to ensure that the fire actually did get going. Just one point I wanted to make: in test 5, the entry door near the kitchen had to be left open in order to allow enough air to get into there to actually allow the growth of that fire. Remember, if test 5 was the test where there were sprinklers, but they were deactivated on purpose in order to allow the fire to give it a chance to grow and reach flashover in the kitchen and become a fully developed fire, and then manually charge the sprinklers to see how well they can bring the fire under control. Of course, test 5 also had the glazing, as I just mentioned. So in order to allow enough air to get in there, that entry door had to be left open. And in addition to that, a decision was made during that test to go ahead and break some of the glazing in order to allow even more air in there to allow it to get started, because it was, even with that door, the kitchen door open, it was still struggling to grow because of the lack of ventilation. So anyway, that the ventilation there was, or the fact that they opted not to put glazing over those openings was simply to allow the fire to grow.
Great. Thanks for that.
TWB opted to do that.
Okay. Thanks for that background, Jason. That's really helpful.
Sure.
Paul, there was a question about firewalls. Can firewalls be used in these new types of construction to increase building areas like we do currently in other types of construction?
Yes, if it's a true firewall, which has a lot of, for buildings of this height, that's going to be difficult to accomplish. But yeah, as for any other type of construction, you can use firewalls to create a new building.
Great.
Build on the other side of the firewall. Yep.
Okay, super. Jason, question about connections, both in the ATF tests and then for design of connections. Talk a little bit about provisions for that.
Sure, and just to clarify, I'm going to answer that question from the perspective of the fire performance of connections as opposed to structural design of the connections, because I think that's what you're asking.
Correct.
So yeah, the fire performance of connections, as Paul mentioned, and he actually showed the provision that's working its way through the Group B Code Development Process and into the 2021 IBC, that states the requirement for fire protection of connections, and that requirement states that connections have to have protection covering them that is sufficient to provide at least the same amount of fire resistance rating as that which is required of the members that are connected by that connection. And I want to stress the point that I made about that's the protection over the connection. That doesn't mean that you can have a fire resistance rated connection per se, although there may be some proprietary designs for a quote-unquote fire resistance rated connection. Really, it's the protection over the connection that gives it its fire resistance rating, and that can be achieved by adding either some kind of non-combustible protection over it, like gypsum wallboard, or it can be achieved by additional wood cover, provided that you're under a construction type that allows you to have exposed mass timber, such as types 4B or 4C, and that's how you can achieve it with the additional wood cover. But it's the protection over the connection that needs to be used to provide that fire resistance rating. And then I also wanted to point out, your question was kind of a two-part question about the connections in the ATF test structure. There were several different types of connections, including beam to column connections and different types of those, also different types of beam to column connections between the glulam beams and the glulam columns. And also there were different types of connections between the CLT floor ceiling assembly and the CLT wall within the ATF structure. And they were all protected as would have been required for the type of construction that each respective test represented.
Great, thanks. Paul, back to you with concealed spaces. We talked about the concealed space requirements for these new types of construction, but I think there's some new provisions separate from the tall mass timber changes for heavy timber, traditional heavy timber in concealed spaces. Can you talk a little bit about that?
Sure. Yeah, unrelated to the tall wood building ad hoc committee changes, there was a change in this past cycle, Group A, that would allow the same type of protection for concealed spaces in traditional type 4 heavy timber as is required for these spaces in mass timber now. And this protection is also mirroring the protection of concealed spaces that's given in NFPA 13, the sprinkler standard itself. So this does open up a new opportunity for concealed spaces if they're protected. That protection would be either lined with non-combustible material, filled with non-combustible insulation, or protected by sprinklers in the concealed space. So that's now permitted for, in the 2021, that will be permitted for traditional heavy timber construction.
Great, excellent. All right, one more for each of you, and then we'll wrap up here. Jason, question about seismic provisions and where we stand with CLT and seismic provisions.
Sure, yeah. The ASCE seismic design subcommittee is working on some provisions that would include seismic design coefficients within the 2022 version of ASCE 7. So that the target is to have it in ASCE 722. That's not a guarantee, but that's the aim. And if it makes that target, then it would be picked up in the 2024 IBC. So that's when you could expect to see such seismic design coefficients and related provisions for CLT design.
Okay. And Paul, last one on flame spread, smoke developed indexes, kind of some existing code provisions for that, but maybe just touch on that as it relates to new tall wood provisions.
Yeah, there's no real change to the required flame spread indexes in Chapter 8 for interior finishes. That would apply to exposed CLT. Flame spread of CLT is easily determined. We have DCA1 document that shows flame spread ratings for particular wood species. So that's not really going to change in terms of flame spread or smoke developed for interior finishes. There is one thing that did change in the last cycle in exit enclosures, since CLT might be used for exit enclosures, but it can't be exposed anyway, so I'm not really sure it serves a purpose, but you're not going to be able to have exposed CLT in exit enclosures. So there was a change to Chapter 8 indicating that in regard to finishes, final finishes for exit enclosures. But other than that, everything will be the same.
All right. Well, excellent. Thank you both for a great presentation. A lot of good information here. Folks, we'll let you go and hope to see you again next month for our webinar, and look for some email from the education team about your certificates. So thank you all, and have a great day.